So, thank you again. The talk is a joint talk with Enrico Oliveira and Eduardo Benzi, and the scope is describing a planning application that we developed for allocating the activity of the AlphaSat mission. So, brief description of the mission. AlphaSat is a commercial satellite that will be launched in the end of July this year, and it will be operated by Inmarsat, so not by ESA. Besides the commercial payload, it also contains 4 so-called technology demonstration payloads that are supported by ESA. So we have, for instance, a payload for 2 payloads for communication technology, one based on advanced laser, another one based on Q and V band frequency. There is a payload actually consisting in a star tracker that is a device for controlling the attitude of a satellite. And finally, there is a last payload that is actually an environment for measuring spatial radiation in space and their effects on different materials and so on. So, as you can see, we have different payloads. Each payload belongs to a different institution or a different group of scientists. So there is a need for not only allocate, but also coordinating the activities, as we will see in a while. And that's where we develop our application. So the talk is basically divided in 2 parts. In the first part, I will give an overview of the problem and how we solve it. And in the second part, instead, I will provide a description of how we put the system into the operational loop. So, going to the problem, I will go a bit top-down now. The problem can be identified by a set of task requests, so different tasks coming from different scientists. Each task can have associated time window, resource usage, and also a weight that is measuring the quality of the reward of executing a particular activity. And then in the problem we have what we can see as resources. So, for instance, the availability of the satellite to actually perform experiments, and also the availability of the ground segment, because for some activities it's necessary to have a kind of teleoperation. So there is actually an operator on ground that is running the activity. So a solution can be seen as selecting a subset of this task and trying to maximize the reward of this set. So one can say, okay, it's a simply oversubscribed scheduling problem. I would say that it's not quite so, even though when we start talking, it looked like that. Why it's not that? Because of something I didn't describe yet. Each task is actually as a logic. It's actually describing the behavior of the payload, of each payload. So, for instance, here in the picture, you can see that for this task, you have 4 states associated to the execution of the activity. So the payload during this, the execution of activities change its states. And also, there are also tasks that can require only onboard execution, so they don't require ground segment support. But what is important here is that we also need, we have in our domain some constraints that are not associated to the task, but are defined on the payloads. For instance, a payload to be in a particular status requires another payload to be another status. So here we have domain constraints or domain synchronization. We don't really have constraints between tasks. Also, we have constraints between the status of a payload and the ground segment or the status of the satellite. For instance, we have cases where the satellite is requested to be off, so it is requested to each scientist to put his own payload in the status off, to switch off the payload. And of course, again, in the problem, we have constraints between tasks at this stage. We have slightly different presence constraints. We have, presence constraints, but are also linked constraints. So you have to execute T1, for instance, here in the slide. You have to execute T1 before T2, but if you don't execute T2, it's useless to execute T1. So they have to come together. And of course, we have resource constraints like bandwidth, power limits, and so on. So, I already said the domain, you can see composed by payloads that can be seen as a state machine, so representing the different states the payload can assume. And also the spacecraft status and opportunity windows can be seen as a timeline or sequence of interval in which is described whether, for instance, the spacecraft is available for experiments or not available, if the ground control is available, if the spacecraft has to be off, and so on. So now I move to the solving approach. The solving approach was developed as a plugin of the ICAPS framework that was developed a few years ago by the group of Cesta, and basically Cesta and Fratini, basically Fratini actually. And what is important in this framework is that it has a capability for modeling, basic capability for modeling planning and scheduling problems, in particular based on timeline representation. And also it comes with some basic solvers like PCP, post-constraint posting scheduler, or basic planner or MPS. And of this framework, we exploit in particular two aspects. The possibility of representing state variables as a timeline, and this, as you can guess, was used to represent the payload's status and the windows and the opportunity windows. And also another component is the possibility of representing resources, so reusable resource like the power and the bandwidth and so forth. So the approach actually works as an iterative repair approach, so constructing a possible solution or allocation of activity, try to identify flaws in this allocation, and then repair it. In particular, we use two solvers to repair the current solution. A planner that we underused somehow, but we use a planner for checking the allocation, so the logic of the allocation. And here, when I say we underuse it, is because by the definition of the mission, we cannot add activities, even though the planner could add it, actually. But we are not allowed to put in the pod new activities. And then we use a scheduler to actually check the feasibility, the time and resource feasibility of the allocation. We slightly modify this scheduler because, as we will see also afterward, we want to not only check if a solution is consistent or not, but in case it's not consistent, we also want to have some feedback, and we want to know why it's not consistent. And this is exploited for driving the search, the solving process. So here I put an example where we have 4 tasks, 2 tasks here allocated on 2 different payloads. And for instance, here we can have a domain constraints that is saying that the status W of A has to be during the status A of B. And then we have another couple of activities here. For instance, we can have these link constraints where we can also specify the minimum distance, minimum time lags, or also the maximum, but not in the example. And then also in this case, we have activities that are representing the allocation on the ground segment, so the use of a real operator, the allocation of the onboard segment, so the use of the satellite, and their actual behavior on the payloads. What I didn't mention before is that actually at the end of the execution of each activity, the state is preserved until a new activity is executed. But for the sake of simplicity, I didn't report it here. So the solving process works like this. For instance, we can have a planning step where we can identify that B1 has to be before A1. If you go back to the example, putting B1 before A1 allows to respect this constraint. And then we can proceed, we can try to schedule, and we see that we have a conflict between A2 and B2, and actually the scheduling is returning the conflict. So we know that the next step is to remove either A1 or A2. And then we have two different paths. In both cases, we achieve a solution. But in this case, again, if we remove B2, we will force to remove also B1, as there is this link constraint. So the best solution, in this case, I assume the weight is 1 for each activity, is this one because it's maximizing the number of activity. And this is actually the final Gantt chart of the solution. So you can see that after the execution of the B1, you're still preserving the status A of the payload. And this is important because you will also preserve the resource consumption, because the resource consumption, that's another bit of information, is associated, again, not to the activities, not to the task, but is associated to the status of the payloads. In each state, there is a different resource consumption, both for power and bandwidth. So this is a brief overview on the problem we solved. But then now I move to the system, how we input the system into the operational loop. Just a bit, the big picture, which are the actors in the loop. We have the entities here that are actually the scientists that are generating requests for experiment on their own payloads. We have the commercial operator that is providing feasibility window. I'm telling you when, they are telling us when we can do experiments. And then in the middle, there is us, what is called the TDP ISA Coordination Office, that is taking the inputs from the two entities and producing a final plan. In particular, the office is in charge of different functionalities, not only the planning and coordination functionalities, but also the telemetry and reception and archiving. But here I will be focused only on the planning. Another request that was given to us when we defined the mission was that the planning process or the planning system has to be completely automated. They don't want, as you can guess, from a budget point of view, budget reasons, they don't want people working behind the system. They want the system completely automated. And the actual operation is based on a week period. So every week we produce a week plan. So this is the initial workflow when we started that they gave to us, the other partners gave to us when we start the discussion to them. And here they foresaw 3 steps, distribution of the windows, the availability windows from Inmarsat to us and the scientists, and then the request, and then us producing the plan. And the time gap here was 3 hours. So what we noticed first was that each TTP, each scientist, has no knowledge on the request of the other scientist. And you see, not only you can have conflict between the requests, but sometimes you actually need to coordinate experiments between different scientists. And also, there is no possibility, once they submit their request, there's no possibility. They receive a plan, they didn't have their task allocated, they don't have any chance to change their mind. So these were the limitations we found, and, but we also have some room for improvements. We don't need 3 hours for producing a plan, obviously, or a schedule if you want. And also, another bit of information that was not known at the beginning was that the windows that they were submitting, they were not covering only 1 week, they were covering actually 3 weeks. They are committing only on the first week, but on the second and third week, they have like roughly 90% commitment on that. So you can actually plan on that information, considering that information. So that's why we propose to change the workflow, adding more iterations, and so to have a more mixed initiative approach. And this triggered a new aspect. I remind you that the system is completely automated. So we need to provide somehow explanation for why an activity is allocated or not allocated. And this is because the scientist needs to know that. And more importantly, because of this iteration, they have a possibility to change their task request. So if we provide some input, they are able to produce tasks that then in the next round will be accepted and allocated. So the explanation method, the approach to generate explanation is based on three aspects, on 3 points. Okay, the most important part is this: to have some labeled decision or informed decision. So we don't during the solving process we put not only the decision in the knowledge representation module, but also information on which solver added this information, and for which reason, or which are the feedback that they can provide. So the more information, the better. And then we have 2 other aspects. Okay, a protocol that is basically a language that we agree with the scientists to communicate with them, and a module for generating from the decision labeled during the solving process an internal representation of the explanation. So I just want to provide 2 examples. For instance, here, these activities cannot be allocated because X is not consistent with off. So here, during the solving process, we found that A has to be removed here, and we know that this has to be removed because of this domain constraint. More complex case is in this one, where you basically you can. It's the same example of before. You need to, because of for respecting these constraints, you want to allocate B before A, but then you cannot schedule because there's not enough room. And then you go ahead, you remove B, you remove A, and then you get the solution. But if you try to go back and see why A was not allocated, at the first sight one can say, okay, because it was not possible to schedule. But it was not possible to schedule because the planner added this. So we have to go back to the planner and understand and try to understand why the planner added this. And this is what we're doing now. So how much time? 1 minute. So I'll skip this. I will move. This is the complete picture of the planning system. So we have a knowledge representation module to represent all the current solution plus all the decisions we are taking during the solving process, a set of engines for modifying the current solution, and then an output generator that contains a module for generating explanation. So the status of the system is, okay, I mentioned before the mission will be launched in July. There will be a commissioning phase, and we expect to be operational next October. During the development, we tested with different benchmarks, artificial benchmarks. But more importantly, we also have different simulations with the real partners. The most recent one was like 1 month ago, and we successfully passed this simulation. So I'll conclude with this if I have time. This is, okay, one step for getting into the mission was to prove that we could actually solve their problem, but that's probably something that is not really new for you, but it was new for them. I mean, you have to consider that they're from a different background. They're not planning people, and they're basically operational people, and they don't have a clue about artificial intelligence, even less about planning and scheduling. What was important during the development was to have a flexible architecture that we could exploit during the development. Why this? Because, okay, this is my previous application was usually done in well-defined problems. This is because usually the mission were already running. In this case, we have a mission that was under definition. And even though at the beginning I was happy because I said, okay, I can influence, and as you see, I influence a bit in the way that it's actually operated now. It was, on the other side, it was really complicated to to keep the pace with all the changes in the mission definition and all the changes in the problem definition. That's why it was useful to have such architecture that can be exploited to change, to cope with the changes in the problem. And for future work, okay, we're thinking about evolution of the current solving approach, also for producing like stable solution. I think one of the reviewers of the paper was actually mentioning the possibility that to keep a stable solution during the 3 iterations. We also want to enrich the feedback provided to the user, and this is going back to the planning capabilities that are not well used at the moment. For instance, we can use, as I said, we cannot generate new activities, but we could somehow generate suggestions. So what comes from the planner can be seen as suggestion to the user. So we can actually suggest why you don't add this activity to your plan. And from a more, let's say, research point of view, what we would like to do is also to follow this path of having informed decision to have a more tight integration between different solvers, planner, scheduler, and so on. And thank you for that.